And here we go. We are recording, and let's talk a little bit about fisheries. All right, a fishery basically refers to a particular species of fish or other ocean life. I mean, it doesn't have to be a biological fish. We can talk about shrimp fisheries or oyster fisheries or things like that. But it refers to a particular species taken from a particular place. So we could talk about the Louisiana Gulf of Mexico oyster fishery, or the Apalachicola Bay, Florida oyster fishery, or the Chesapeake Bay, Maryland crab fishery, or the North Atlantic particular species harvested in a particular place. And that's quite a lot. As of 2016, we took an estimated 171 million tons of fish and seafood from the ocean, 88% of it for direct human consumption. If you're wondering what we did with the rest, just by way of an example, there is a small, rather oily Atlantic fish called the menhaden, and it's not particularly delicious as far as I know, but it can be processed for things like a product called fish meal, which is a source of protein that can be added to things like cattle feed. Other fish can be added to various fish extracts that can be used for fertilizer, things like that. So we don't eat all of it, but we eat an awful lot of it. And as of 2014, the global value of all fisheries was estimated at $270 billion, which is kind of a lot. When you go fishing for species in the oceans, we divide those species into stocks, which are mostly isolated populations in different habitats. One example that's pretty easy to grasp is Pacific Coast salmon. You might remember that salmon eggs hatch in streams in the Pacific Northwest, and the developing salmon larvae, the little fry, drift downstream, end up in the oceans, grow there for, I think, anywhere from 3 to 10 years. And then once they're fully sexually mature, they swim back upstream to spawn. And if they make it up there, they'll spawn, they'll die, and then the next generation hatches and drifts downstream, and so it goes. Salmon, if you recall, have such good senses of smell that most of the time a salmon will return to the very stream where it was spawned. Even though they're all in the ocean together, they don't just go swimming upstream at random. They will swim upstream up the same river where they were born and where they came down. And the upshot is that there's, I think, 5 species of salmon that are commercially fished on the Pacific coast, but we can divide them into something like 20 different stocks, because the salmon that in the Columbia River between Washington and Oregon don't usually interbreed with salmon that spawn in, let's say, the Eel River in Northern California. They spawn in different rivers. They're genetically a bit different from each other. There may be a little bit of crossbreeding between them, because every so often a salmon does get lost, but it doesn't happen all that often. So the populations are isolated. They spend at least part of the time in different habitats, and things that affect one population don't necessarily affect the other in the same way. A dam on the Columbia River might affect the Columbia River salmon, but not the Eel River salmon, who are spawning in a different river, and so on. And so we can divide up these salmon into different stocks. Sometimes they're identified by the use of physical tags. You fish up a salmon and staple a metal tag to it, and if that's ever found, that will tell you where the salmon has gone. These days, you can put tags with a radio emitter that can be tracked by satellite, and you can also do genetic testing on fish or other organisms for genetic markers that might be unique to a particular stock. We can try to estimate the stock size in various ways. It's often estimated just measuring the number of fish that are caught. That's the number of landings, as in, well, if you've ever gone fishing, you know about landing a fish. And landings are in part a function of population size, but they're also a function of how intensely a species is being fished. I mean, if there aren't any landings of a particular species, it could be because the species is extinct. It could also be that nobody is trying to catch it. So you have to factor in both population size and effort put in. What you're looking at is data for the Japanese fishery for Pacific salmon in the Bering Sea, the sea between Russia and Alaska. Up at the top, that's the number of vessels that were participating. As many as 500 Japanese fishing vessels went after Bering Sea salmon in, looks like 1955. Down below, the data you're looking at is number of tons of nets that were used. And you can see that the bar number of vessels showing the mass of nets parallel each other pretty well. And these are just two different ways that you could measure effort. And you can see that Japan, between about 1955 and about 1990, the trend has been to decrease the amount of effort it's been putting in to fishing for Pacific salmon. Part of the reason is that the fishery is partly in United States waters. And in 1972, under the Nixon administration, the U.S. passed the Marine Mammal Protection Act, which started limiting Japanese fishing because it was killing lots of dolphins. So you can see there's actually a little fall off in 72, and it kind of goes downhill from there. Fishermen will, if they can't fish in one particular place, they may just shift efforts to another region. And I'm assuming that's what happened there. Probably a better estimate is catch per unit effort. This is a measurement of thousands of tons of fish per million tons of nets. So you calculate the total mass of the fish that you take divided by the total mass of the nets that you use to catch the fish, and you get a better estimate of fishery trends that isn't affected by fluctuation in efforts. So you're looking at here is the thousands of tons of fish per million tons of net for the Japanese drift net salmon fishery between 83 and 89. There's a dip in 1986 because of political factors that nearly closed off the fishery. That measure of effort went from, looks like about 5.4 to 3.4. So I guess they lost more than a third of their effort. And fisheries, of course, change from year to year. The amount of effort may change, politics may change, but the amount of available fish or other species that can be caught changes from year to year. And that's equal to the preceding year's size minus the old fish that have died, plus the new fish that have entered, plus the growth of the existing fish. You don't have to memorize that equation, but delta W is changes in a fishery size measured in terms of weight, measured in how many tons of fish there are to be caught. It's equal to WT minus the mortality of last year, the number of fish from last year that died, plus the recruitment, the number that have entered, plus growth. Recruitment, by the way, refers to new members entering, and it could include just reproduction within a population, but it could also include dispersal. It could also include new members that are migrating in from somewhere else. If more migrate out than migrate in, you could have negative recruitment. Whether that happens or not depends on what species you're talking about. And since you want to keep track of changes in the size of a fishery to know if suddenly there's lots more fish or fewer fish, you have to be able to estimate all of these. And to estimate these, you have to calculate the ages of a sample of a population. If a fishery has lots of very old fish, that's one thing. If it's all new fish, that's another. And we can do this with fish by looking at little blobs of calcium carbonate that build up in the middle ear. These are used in the part of the middle ear that regulates balance, and they're called otoliths. And the thing about otoliths is that, like tree trunks, they grow in growth rings. Layers of calcium carbonate get laid down on the outside, and the otolith gets bigger over time. You can do this with freshwater fish too. In fact, if anybody's worked much with the Adamses, they've done some otolith studies on the freshwater fish populations that they specialize in. So this applies to freshwater as well as marine. Those opaque zones, the ones that look darker, grow more slowly. That's a time of slower growth, so it's probably winters. The lighter zones represent faster growth, so that's probably summers. So it looks to me like this fish has gone through 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like this fish is maybe 11. Am I that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, maybe it's 10. Nah, maybe it's 11. Okay, whatever. The cool thing about whales is that whales don't have otoliths, but they do have earwax. Whales have they're mammals, so but the earwax ends up plugging the ear canal, and that also tends to build up in layers. So what you're looking at here is a 10-inch long plug of earwax that was taken from a male blue whale that died in 2007 after a ship ran into it. Nobody actually went out and killed this blue whale. It was accidental. But since it happened, scientists were able to try to get some data on how fast blue whales grow by extracting that earwax plug and cross-sectioning it and counting the layers. And it's estimated that the blue whale was 12. So from data like that, we can, you wouldn't want to kill too many blue whales to get this, but from data like this, you can try to make some stabs as to, how old the members of the population are and how fast the population might be growing. Why does that matter? If you've had ecology, you might remember this. If you haven't, I think we mentioned it at a much earlier lecture, is that if you watch the way a typical population grows, it'll start out small. Since it grows exponentially, the rate of increase will go up. It will increase faster and faster and faster. And then the rate of growth begins to slow down. And eventually the population levels off at the carrying capacity, right? I'm assuming everybody remembers that from, I think that was when I was still doing in-person lectures that we covered that. Here's the thing. If you've had some calculus, you might remember derivatives. You might remember that for any point on a curve, if it's a well-behaved continuous curve, we can calculate the slope of the tangent line, the slope of a straight line that touches the curve at that point, and that gives you the instantaneous rate of growth. That gives you the rate that the population is growing at that particular moment. So you can see a couple of places where these tangent lines have been drawn, and right in the middle at k divided by 2, that's where the tangent line is steepest. That's where the curve has its steepest slope, which means that's where the population is growing the fastest. That, in theory, is the maximum sustainable yield. If you want to know how many fish to take out of the population, if you knock it down to k divided by 2, if you take half the population, that's where the rate of rapid and the population will recover most rapidly. If you take almost all the fish except a few, it will take much longer for that population to build back, right? Because, if there's only 5 fish left in the ocean, their numbers will eventually double and quadruple and eighttuple and so on. But it will take them a long time to recover. That curve at the very beginning is not very steep, and it takes a while for it to build back up. If you take a very small number, the population won't increase very fast because that curve is very flat. If you take no more fish than k minus 2, the population will recover the most rapidly. There's a bit of an extra wrinkle. Imagine you take all of the fish except 5. In many populations, it might be very hard for those 5 fish to actually find each other. If you have millions of fish in an area, then probably just about everybody is going to find a mate at some point. All right, it may not be their high school sweetheart, but there's lots of fish in the sea. That was a joke. If you have large numbers of fish in an area, it's very easy to find possible mates. If everybody is completely scattered, and you've got, 10 fish in that area, mates finding each other is going to be more rare. The same reason why it's easier to get dates in Little Rock than in Judsonia, for much the same reason. The upshot is that when populations are small, recruitment is lower than expected because males and females can't find each other. What you're looking at here is the first derivative of the logistic equation. If you haven't had calculus, this is a measure not of how large the population is, but of how fast it's growing. At 0, the population is holding still. Positive values on the x-axis mean the population's growing. Negative means the population is shrinking. And if you look below the graph that's labeled no alley effect, the population is growing fastest at 1/2 of k, right? It is growing the most rapidly when you're halfway between k and the origin. That's where that curve has its peak. But if you've got a situation where populations are small and recruitment is low, the situation is strong. If we take the population down almost to 0, the population will actually shrink more, right? Because that red line is below the x-axis. That means the population goes down. And the reason is if you knock out all of the fish except for a small number, they're going to have a hard time breeding because they can't find each other, and that population may drop even further. You don't have to kill every last member of that population in order to set it on a trajectory towards extinction. And again, this phenomenon in small populations is called the alley effect. And in populations where the alley effect applies, you can see the maximum on that strong alley effect graph. You can see that the maximum of that first derivative curve is closer to k than halfway. You can't fish all the way down to K/2 if you want the population to recover as fast as it can. Another population, and one that we mentioned way back, is people tend to like catching big fish. It's not only, it's more fun if you're a sport fisherman. If you're a commercial fisherman, it probably means less effort. You've got fewer fish that you have to gut and process. And fishing techniques may preferentially take larger fish. There may be a legal size limit. There may be a minimum size of holes in the net, for example. The idea being that if you take the small fish, you're taking the juveniles that will grow into big fish later. And if you take the small fish, you're cutting off that population's chance of growth. Bye, sweetie.
Bye.
All right, my wife's on her way out the door. All right, have a good time.
You too.
All right. All right. Okay, my wife says hi. And this means that a number of fish populations are maturing sexually at an earlier age and smaller size. So in Atlantic cod, the age at sexual maturity has gone from about 7.5 years in 1950 to 4.5 years in 2010. And it's plain old natural selection. If you grow and grow and grow and get really large before you mature sexually, you're likelier to get eaten. If you sexually mature really fast before you've had a chance to get large, greater reproduce before the humans catch you and eat you. So fish that mature early and have a small body size are more likely to reproduce than the ones that get big. So in Atlantic cod, you can see that age at maturity has gone down quite a bit in 60 years. The same for American plaice. That's a flatfish related to flounder and sole, and very tasty. And you can see the age at maturity has dropped from 11 years in the 60s down to 7 years in the early aughts. So this is a problem where humans are unconsciously exerting natural selection on the species that they capture. Another problem with fisheries is bycatch. Bycatch refers to everything that you catch other than the fish that you were trying to catch. If you're fishing with a net, if you're fishing with a bottom dredge or something like that, you'll catch things that you weren't intending and that you can't sell and that maybe don't taste particularly good. Here's some bycatch that's been discarded, maybe dumped back into the ocean or tossed on land, but either way, it's usually killed. The highest bycatch ratios, by the way, are tropical shrimp. The average is 5.7 kilograms of bycatch are caught and die for every 1 kilogram of shrimp. I don't particularly want to tell people what they ought to eat. It's not really my place to do that. But those who are concerned about the long-term welfare of the oceans, do what you can to reduce your consumption of Asian shrimp. No offense intended to countries like Thailand, but this is not the kind of thing that we can keep up. There are some traditional ways of making use of bycatch. If you ever go to the French Riviera, you might get to try this in a restaurant. This is bouillabaisse. And traditionally, it's made of bycatch. Fishermen would go out, catch whatever they could in their nets, sell the large and tasty fish to bring in money, and instead of discarding the bycatch, they had traditional ways, they still do, of preparing it for their own consumption. They're eating what they can't sell, and they've managed to make it taste absolutely delicious. So sometimes bycatch is edible, in some fertilizer. into fish meal or into fish emulsion, which you can actually buy in garden stores to spray on your plants. But a lot of bycatch is discarded when it's dead or dying, and this is a potential problem, especially because bycatch frequently takes air-breathing animals. Whales, dolphins, seals, and sea turtles are all dependent on breathing air. And if they're held underwater by blundering into a net, they drown. You can fit devices into nets that take advantage of bycatch species size or behavior in order to give them escape. What you're looking at is a turtle exclusion device. These have to be fitted to shrimp nets. These have been fitted by law since the 70s to shrimp nets in the Gulf of Mexico shrimp fishery, for example. They provide a way for turtles to quickly get out without losing too much of the shrimp. This is the way they work. There's an escape opening midway along the net. Shrimp, there's that grid that you see right there in the middle. The shrimp and small fish can pass through the grid. Turtles and large fish can push their way out of the escape opening up at the top, and that escape hatch will fall closed behind them. So that decreases the bycatch of turtles and also of large fish. In this diagram, there's a big ray that's coming out of the escape opening. That's that diamond-shaped thing right there. Gulf of Mexico fishermen did not particularly like having to have one of these put on, but with better design, they've been able to minimize deaths of sea turtles while still bringing in pretty good shrimp. I mean, the Gulf of Mexico shrimp fishery is still one of the fun things about growing up in South Louisiana is, you know, some places have ice cream trucks. We had shrimp trucks, trucks that had just driven up from the fishing ports on the Gulf of Mexico with fresh shrimp, and they'd call in advance and then deliver, you know, 5 pounds or whatever you wanted to buy, or they'd sell it by the side of the road. Problem with ghost nets. Fishing boats sometimes lose their nets. They may have to cut them free. They may fall off because of mechanical breakage or carelessness or something like that. And the problem with ghost nets is they can drift through the ocean for years. Everything in their paths may be trapped and killed. So this is an environmental problem. I'm not sure I have a particularly good solution, but it's certainly something that all countries need to work on, is minimizing the incidence of ghost nets. And when I say nets, I don't know if you're thinking about, you know, a dip net that you might use for fishing in a lake, but commercial fishing boats' nets can be miles in length. You know, they can swim around and lay down a circle of netting or a panel of netting that may be several miles long. Remember that graph that we started this lecture with? Those fishing boats were laying out net in, what was it, millions of tons. That's an awful lot of net. So we're not talking about just a small section. We're talking about possibly a mile-long panel of net drifting through the oceans. Anything caught in it, well, it's a net. The point is to catch things so they don't get away. And too often, they don't get away. So I've not got a great solution for that, but that's one of the problems that conservationists have to deal with as we work to try to conserve the ocean's resources. You know, we can't stop fishing. Too many people are dependent on what the ocean can provide, but with any luck, maybe we can figure out how to do it more wisely. All right, I will now stop Recording.